So first I'll say thank you to Ian and Reza for inviting me and having me. Second point is I thought I brought the weather with me from Florida with some rain, and I checked tonight it's going to be like 20-something, and that's not Florida weather, so I won't take credit. Thirdly, I have this pointer, and I'm pretty young, so I've never actually used this kind of pointer. I'm still looking for the button. And I think that's probably it to start. So I appreciate you coming. I told Sarah I may have picked too simple of a title. So the crowd is kind of full, and maybe if I pick something scarier as a title, not as many people would have come. But really what I hope to do is just give a pretty high-level overview of my work and interest in magnetic materials, and I'll talk a little bit about the motivations of why we want to study this, particularly for MEMS and microsystems. I'll talk a little bit about what I call technology development. This involves some element of materials and fabrication. And in the end, I'll give you some examples of how we use these magnetic materials for functional applications and devices. Specifically, microactuators, some vibrational energy harvesters, and then something called a magnetic undulator first, X-ray generator. So I think most of you know a little bit about MEMS, and so integration of electromechanical functionality. And there's innumerable ways to implement this, and different transduction schemes, different materials, etc. We kind of hone in on electromechanical transducers. We're generally trying to convert electrical and mechanical energy. And in MEMS, the most common ways of doing this, if you survey the literature, is electrostatic or capacitive methods, thermal methods, piezoelectrics. And if you find the most unpopular way to do this is what I'm most interested in, and that's with magnetics and what I call electrodynamic interactions. And so the question when I was in my PhD was sort of why? Is there some reasons not to do this, or is it just not mainstream, or what? So I'll kind of lead you through my arguments of why I still think this is useful and interesting, and some of the challenges of why this magnetic devices are not so common now. So the first kind of misconception I want to dispel is some people think that if we make a tiny magnet, the fields from the magnet gets weaker and weaker as the magnet gets smaller. But that's actually not true. If you consider that if we have a big magnet and at some distance, it makes a field of, just make up a number, 0.2 Tesla. If we make the magnet smaller and smaller, as long as we keep the relative distance away from the magnet constant, the field intensity remains the same. And this scaling goes down to about a micron length scale, below which you run into all sorts of nanoscale things, which are interesting in their own realm for other reasons, but maybe not for microsystems. So magnetic fields scale pretty much independently. We can make small magnets and still create Tesla-level fields with the right materials. And then we think about magnetic transducers, and you look around in your home or your car, and pretty much everything that's not a microsystem uses magnetics. So your speaker, your window thing that moves your windows up and down, starter in your car, the Hoover Dam, hydroelectric generator, the rest of the world at macro scale is based on magnetics. And the reason, some of the reasons are, for actuators, we have generally high stroke compared to, say, an electrostatic actuator. That's beneficial for valves and pumps and other things. Pretty moderate force and energy densities. The transduction schemes are linear, so there's no silly complications. Like capacitive transducers, you have to linearize some other things. But they're contactless, so magnetic fields can reach out over modest distances. They work both as electromechanical and also mechanical electrical transducers. So all the benefits you'd want in a transducer, and then compared to, say, piezoelectric and capacitive devices for system integration, generally they're more high current, low voltage devices relative to, say, piezoelectrics. We also know from everyday life that they're functional over very wide temperature ranges generally, hundreds of degrees Celsius. They meet automotive specs, military specs, and they're known to be robust. Most of the time, the thing that fails in your car is not an electromechanical motor generator in your car. It's maybe some electronic component or something else. So I would argue they're robust. But as I kind of mentioned earlier, the magnetic MEMS are still emerging. So I'm going to define a few things here. These are basic physics and magnetic interactions, and the reason I do so, you'll see in a minute, is because some of the scaling laws differ. So the first one I'll define is what I call electrodynamic transduction. This is a classic transduction terminology. And this is basically the F equals VLI, you might remember from physics. So if you have a current carrying wire, and it's placed in a transverse magnetic field, there's some force on that wire. You can use that for actuation. Conversely, if you drag a wire with some velocity through a magnetic field, it will induce a voltage through Faraday law of induction. And so this is commonly used in loudspeakers, hard disk drives, the little read-write head that swings out in modern applications today. So that's electrodynamic transduction. Slightly different. The physics are kind of related, but they're a little bit different is what I'd call magnetic transduction, not to be confused. And this is the idea where you have an iron core, and you can energize that core with a winding, but it's the tendency for this other iron plate to close that gap. In fact, this mechanism is much more similar in its physics and scaling to a capacitive type transducer. So we'll call that this, magnetic transduction. The force you get here is a very different equation from what I showed you before. It's a tendency to close that magnetic gap. And this is used historically in telegraph receivers, solenoids, and other simple kind of doorbell type actuators and other things. Another thing we can do with magnets, and this doesn't do any transduction, but even my young kids know that magnets stick together, and there's lots of fun things you can do with that at very different size scales. And so just for a magnetic latching, so you want to make a bistable valve or something, you can maybe actuate the valve and have it stick in one position, actuate it and have it stick in the other position without any power draw in the two different states. So we can think of ideas and areas where we may want to use interaction between two permanent magnets. And so then we make some friends, and this is a nice French group who happened to host me for my sabbatical a few years ago, but they like to make it very simple. And even at 4 o'clock on a Tuesday, you can figure this plot out. And so this is a plot of some interaction between magnets and currents and how they scale. We have a system, and we scale everything down by some, call it shrinkage factor, K. K is a size scaling factor. What happens? So the first example I showed you is electrodynamic transduction. Basically shows no scale dependency. There's no penalty in the force per unit volume of which you can actuate things. The actuator authority is break even. So no benefit to going smaller, but also no disadvantage. Magnetic transduction, on the other hand, actually has an unfavorable scaling, just from simple scaling laws. And so most of the, actually what would be called magnetic MEMS that you find in the literature actually make use of this magnetic actuation principle. There's usually a coil with a soft magnetic piece of iron, and they're trying to actuate that iron. And unfortunately, that just doesn't scale very favorably, just from dimensional scaling laws. Hence the frowny face. And then the other thing, though, that I picked up on and we use for other purposes now is that the interactions between two permanent magnets actually has a very favorable happy face with double star eye kind of beneficial scaling law. So I saw that, and even as a grad student, I knew that might be important later. And so I'll come back to that a little bit later. So bottom line is, if you go back to this chart, interactions between magnets and iron and currents and iron are maybe not so good. But, magnet and magnet current is favorable. So the big challenge here is we need permanent magnets. Okay, that's a challenge that we'll talk about for the next part of the talk. But I wasn't the first one to discover this. Even back, when I was, I guess, still in high school. Henry Guckel is a pioneer in the MEMS field. He made some of the earliest mechanical motors and things, which you probably see in your MEMS textbook. He says permanent magnets are vital to magnetic actuation, but their integration still needs to be mastered. So he's pointing here at the problem of integrating and microfabricating. That's the real challenge here. It's not the physics. Nora Dempsey, a colleague of mine in France, again, sort of 10 years later, repeated what Guckel said in that paper: need for both good magnetic properties and integrated magnetic fabrication process hasn't been done. And so I took that as an open challenge. This was my Ph.D. graduation day, and I said, this is the problem I want to work on as a junior faculty. And so we look at now, why is that? Why can't we make high-performance magnetic materials, permanent magnet materials, at wafer level fabrication? And really what it comes down to is the problem for all microfabrication. It's this trilemma between process constraints, material constraints, and then the necessary geometries we want. So let me try to unpack that. Process limitations, you go in the clean room, you predominantly find vapor deposition tools and maybe electrochemical deposition tools. So when you think magnetic materials, many of you think in iron, nickel irons, things like this. These we can electroplate quite readily, but those are all soft magnetic materials. A soft magnetic material is like your refrigerator, and a permanent magnet material is the permanent magnet that sticks to the refrigerator. And so for permanent magnets, it's very hard to deposit them with vapor deposition, and some of the best performing permanent magnet materials you can't electroplate, as it turns out, from simple aqueous or water-based baths. Materials, the materials are limited by the deposition process. Of course, you can sputter lots of things, but oftentimes the stoichiometry isn't maintained. And really, what the big problem is to get good magnetic properties at bulk, the way they make macroscale magnets, there's all sorts of fancy metallurgical tricks they do. They cold quench the materials, they hot roll them, they deform them, and they do different things to create micro and nanostructure features in the material itself, which give rise to the desirable magnetic properties. We can't do all that fancy business that easily in kind of a traditional wafer semiconductor platform. Now, the other problem is that we also, for functional devices and things I'll show you later, we need magnets that are fairly thick. We don't just want a little nano layer like you might find in a hard disk drive. We need a very thick 10 micron thick film or thicker to do functional devices. And then coils, they're a headache on their own because of their three-dimensional nature. And so coils I won't talk a lot about, but this was kind of solved. With enough brute force, you can go make very complex coil winding with electroplated copper or gold or other things. So I think this is kind of a somewhat known route. But then we get into the magnetic thick films. And so as I mentioned, soft magnets, it turns out the best performing soft magnets in bulk are these alloys here, and we can very easily electroplate them. So that's kind of solved. But the really hard part was the hard magnets or permanent magnets. And so what the options you can look at are electroplated metal alloys. And so cobalt nickel, they're really meager magnets. And then there's these platinum alloys. So I'll talk a lot more about this cobalt platinum alloy, which has some very unique properties. You never find a cobalt platinum magnet on your refrigerator though, because the platinum is a little bit expensive. And so in macro scale systems, you don't find this material, but it actually is fantastic for microscale systems. We can look at what's called the rare earth magnetic materials. The two most popular ones are something called samarium cobalt alloys and neodymium iron boron. These are very standard. Even though they're, quote, rare earths, they're still very abundant, and you can go buy them online for 10 cents. They're not that rare. And you can sputter these materials or pulse laser deposition, but they're complex. And the problem with these materials is that the rare earths tend to oxidize very readily. And so for thin films, you can deposit them, but they're very susceptible to corrosion and oxidation. So that's not good. And then there's also this idea of using powders. Why can't we get micro powders or nano powders and somehow figure out how to get them in the clean room? And as long as the clean room manager doesn't meet you at the door, there's maybe a possibility there. So, part one sort of done. So let's move forward. And I'll talk about now the materials, and I'll just give you a heads up. I'm also going to talk about once we can make magnets, because you'll see we can make magnetic films. So I'm going to also show you how we can then pattern those magnetic films into very complex poles or pole patterns, which is also an additional step.
Can I ask a question about the previous slide? What is the approximate magnetization between those different materials for the hard magnets that you're talking about? So is cobalt platinum particularly?
This is the best. We'll just call that a 1. This is about 80% of that one, and these two are about equal actually. This is like a 1 or 2, or this is a 10. Let's make this 10. So this is like 1 or 2. These two are 8 or 9. This one's an 8 or 9. I'll better define those numbers.
That's what I was looking for.
Try to keep it simple. All right. So what do we want for a thick film? If you're a MEMS person, you want that, or anybody, you can do this. And material science people know how to do magnetic properties, and even mostly fan films, but you can find occasional paper where somebody does a really thick film. For materials paper would be maybe a micron. And stress is important, low cost, of course. But oftentimes these sort of more fundamental materials and condensed matter physics paper don't really address the microfabrication issues that we also need to figure out the integration part. And so we want the process hopefully to be fast and simple. We don't need some $1 million tool to do the deposition, because then only one lab can do it. We ideally want the process of deposition to be low temperature, if we can avoid it. We need to be able to pattern, like structure the films of different shapes and control the dimensions, of course. We also want the films to be chemically and thermally stable after they're deposited, because of course that magnet's going to have to go through other process steps after we put down the magnetic layer if we want to build a device. All right, so back to Sarah's question. I'm going to introduce some terms, and if you're not familiar with them, don't fear. Magnets are characterized by two loops. They're related, but the first one is the magnetization as a function of the applied field. So you guys have probably seen this sort of S-shaped, what's called hysteresis curve. And the main figure of merit on this curve is something called the intrinsic coercivity. And this is the amount of negative applied field H that causes the magnetization of the magnet to go back to zero. It's how much field does it take to overcome the residual magnetization of the magnet. And so that's kind of how strong is the magnet to becoming demagnetized, if you will. The other curve is used more by engineers, the BH loop, and it looks fairly similar. I won't get into the details, but there's the remnants. This is the one you probably see on the website when you go order a magnet. This is when you buy a magnet. They call it a 1 Tesla magnet or a 1.2 Tesla magnet. That's what they're talking about. And then another figure of merit that if you just want to track one number for goodness, what I was alluding to before, is something called the maximum energy product. And it relates to how much energy the magnet can supply into a gap. So without going through all the details, it's just the main figure of merit for quantifying the performance of different permanent magnet materials.
What about squareness of the loop?
So yeah, the squareness is important. I won't discuss that here, but that obviously will factor into what the remnant value is in the energy product as well. So the first thing I'll talk about is this electroplated cobalt platinum alloy. So you can actually electroplate this cobalt platinum and iron platinum alloys. We've spent most time doing cobalt platinum. It's a fairly tricky bath. There was some work we adopted from some other groups and improved on. But the bath here, if you've done any electroplating, is fairly complicated. You have a source of platinum, a platinum salt, a cobalt salt. You have a couple additives to control stress and a few other things. To do some other electrochemical things. You control the current density, the pH, and the temperature of the bath, and you basically just selectively electroplate it. It's a fairly simple process once you get the bath chemistry and the plating parameters done. And so here's a picture of just, say 10 micron magnets. These are the magnets. They've been defined by a photoresist mold, and we can control the size and shape of the magnets and grow them quite thick, tens of microns. Some properties, just to give you some idea, these are actually an 80-20 ratio, what's called the cobalt-rich phase of cobalt platinum. And the nice thing about these magnets is they give their strong magnetic properties in the as-deposited state. You deposit them, and they're ready to go. You do a pulse magnetization process. You have to apply a single strong magnetic field to pull the magnets or magnetize the magnets. But at that point, with no further work, they're ready to use. And these magnets in particular have an out-of-plane texture, so their desirable properties are perpendicular to the substrate. So they give better out-of-plane magnetic fields. So here's a particular curve for 150 by 150 microns, 18 micron thick magnets, and all the numbers. If you know what these mean, hopefully it'll make sense. This figure of merit down here is, if you just want to track this one, the gold standard of what's called bulk-centered neodymium iron boron. The gold standard right now, that number is about 400 for reference. And so our magnets are pretty good compared to the state-of-the-art in bulk materials. And these have remnants of about a Tesla, and of course it'd be about a third of Tesla. Another alloy we did was an equiatomic composition of cobalt platinum here that's 50-50, and you do an annealing step at 700 degrees. This is my first strike. We're using high temperature now, but we can actually get better properties with this alloy after annealing. You transform the disordered cobalt platinum film into an ordered array of the so-called L10 structure. And these give very favorable magnetic, very square loops again with even better properties. So the coercivity here is almost a Tesla, remnants 0.8 Tesla, and the BH max about 150.
Can you comment how we measure these loops?
Good question. So all the loops are measured with a machine called a vibrating sample magnetometer at room temperature.
And the magnetization field you took into account?
Yes, this is actually the raw data with no demagnetization, correct? And we have, these are in plane and out of plane. So these materials actually are fairly isotropic. This particular material is isotropic in nature. There's no texture, perpendicular texture.
If I understood you correctly, you talk about thin films, yes? It's vertically magnetized.
Yes.
And the charges will create a very strong demagnetizing fields, which degrade the performance of the magnet. Can you comment on this?
Right. So that's why the difference here you see for the in-plane curve in red, the demag effect that you're talking about here is the difference in this black curve here. That's the discrepancy there between the raw measured in-plane and out-of-plane properties. There's some columnar striation. I mean, if we can go into certainly more detail, if you look on a cross-section, you'll notice the out-of-plane, there's some actually microstructural columns that form, and so this also helps give some shape anisotropy, not the standard thin film, the full demag that you might expect for a traditional thin film, where that out-of-plane magnetization curve might be very flat.
So what's the impact of the annealing to the top surface? Because I see all those roughnesses at the top. What order are we talking about?
Yeah, so the surface roughness here, you do see this, the surface does get rougher, and that is associated with this phase change. There's also some cobalt segregation. So you actually get a cobalt platinum pillar, and it's surrounded by a grain boundary, a cobalt-rich grain boundary, which actually helps enhance the magnetic properties. Because I think that's why we see this type of polymer structure.
What is the curate temperature of this material?
This one is about 560 Celsius.
And quick question over here.
Yeah.
If you're going to talk about it later, great, but how does this compare to the bulk properties of the material? So if you took the same material and just made a magnet that's a centimeter
Of
by
this
2.
alloy?
Yeah.
This is pretty close. I think the bulk properties for this is like 225
Okay.
for pH max, if I remember right. It's close. It's not quite there.
Okay.
Part of that's because we have some cobalt dilution here. This was about 10% cobalt.
Oh, so you know the reason? The reason is that there's this extra impurity in it, or
Well, the reason was when we deposited the original electro deposit, we just ended up with slightly cobalt rich,
I see.
which was unintentional at the time. We can go back and retune the product with that chemistry to get it.
I see.
right on.
Okay, and that explains most of the difference. It's just that you didn't have the right ratio of materials.
I won't say it explains all of the differences.
Okay.
It gets quite complicated. Maybe we can have some more
Okay.
offline discussion later.
All right. Cool. Thank you.
Yep.
So you will heat them at annealing above curate temperature, yes?
Yeah, so in this one we cycle it at 700 for a 40-minute anneal, and then when we cool it back down, you actually induce a phase transformation in the crystal lattice, and then they exhibit as the positive curve is it's a very narrow hysteresis curve. It's almost like a soft magnet.
It's done in the presence of a field, magnetic field.
No field, no field.
So if you heat them above curate temperature, there was magnetic property. There is no remnant magnetization.
Correct. So applying the
What
field would help.
causes it to have uniform remnant magnetization on annealing?
Uniform magnetization.
You
I'm not
want-
sure.
You don't want the main structure. You want the whole specimen magnetized uniformly. Yes?
Okay, so after the fabrication, we would take the magnet and we would pole it. We put it in a magnetizing fixture and put a single pulse field, just a quick pulse, to pole the magnet, either out of plane or in plane, whatever direction you
So
want
you
to pole
apply
it.
magnetic field.
Yes, yeah, at room temperature, after
After annealing.
the, correct, that's correct. And when you do these VSM loops, this is the applied field. This is the magnetization as a function of that applied field. That's what you're exactly tracing out in that case. So if we want to just simply measure the material properties, we sweep the magnetic field up to a large positive field, so we go up to here, and then we do a negative field, and then back to a positive field. That traces out that whole loop. If we're just in the business of batch fabricating the magnets, we don't have to do that. We just do a single blast to a high positive field and pull them out.
And how is this three figures of merit, remnant magnetization, coercivity, and squareness of this cobalt platinum film compared to the neodymium iron boron magnet?
Okay, good question. Since you asked, I'll go. Here's the second quadrant curves I don't show the whole loop, it'll be down here. The three kind of common alloys that you find, 2 samaric cobalts and then neodymium, and I'll overlay our results on it. So there's our blue is bonded magnets, which I haven't got a chance to talk about yet. The pink was the cobalt-rich phase, and this orange line here is this L10, the annealed magnets. On the same kind of apples-to-apples comparison. So traditional cheap, like refrigerator magnet, or on something like kids' toys, what you might find would be a ferrite, very low-cost ferrite magnet. It's way down here. obviously, the bigger the better out this way, the better the magnet. So if I may, let me go back and talk about powders. Another thing we've tried to do is to use magnetic powders because they're commercially available in all sorts of different material alloys and size scales. And so we can go buy rare earth powders at different microscale powders and find ferrites and other things. And so a lot of people have mixed the powders in with polymer resist and try to spin coat them in things. But usually when you do that, you don't get very high magnetic powder loadings. Because when you put a lot of powder in a fluid, it turns out more like a toothpaste and not like a photoresist. And so what we've done is try to do a dry process. It's a little bit untraditional. So you take a silicon wafer, maybe etch a deep cavity in it with DRIE, and then we dispense the powder on the surface and just do a doctor blade technique to literally just scrape the powder into the trenches, all just dry, raw powder. And then we have a number of ways we can bond the powder into place. One is with a vapor deposition of a polymer like Paralink C. We've also done spin-on polyimide. There's a number of ways we can bond the powder into the cavity. So this is a picture of a full wafer showing the pattern transfer. The little circles are different magnets embedded in the silicon substrate. Here's a cross-section of a different wafer. The full wafer thickness. We can make very deep magnets, 300 micron tall magnets. The magnets that we make here are fairly isotropic in nature. But this process is very fast. We can make we're not limited to waiting for a very long deposition time to fill up this cavity. It's literally just kind of scraped in there, grad student razor blade style at this point. But we've talked to the manufacturers who sell tools that do this in an automated fashion, in fact. So here's some pictures of just a random example. We've done all sorts of different powders here. This is some very spherical neodymium-ion boron powders. They're 50 micron particle size. And these are the particles. This is what a pattern substrate may look like. And this is a cleaved cross-section, so you get a feeling for how well filled the trench is. It's very filled. It's fairly uniform. And this is the one where it is parylene vapor-coated. And if you cleave the wafer, you can actually, the parylene comes in and actually infiltrates down through this matrix and puts like a shrink wrap coating on all the particles. So all the particles are held in place. When you cleave it and tear it, you can actually see these white spots where that shrink wrap polymer coating has been torn away, for those of you that don't know what parylene is. But one limitation of these monodispersed spheres is you get a lot of void space and a fairly low fill fraction, maybe only 40% by volume. So we can go back and do the standard material science trick, and we try to fill in those cracks with a smaller powder, in this case a 15 micron powder, to help fill in the void space. And looking just over here again, the second quadrant magnetization curves. Just the 15 micron powder is here, the 50 micron powder here. When we mix them just in a 50-50 ratio, we can increase the remnants because we're increasing the volume fraction of the magnetic material. And so for that particular, this particular example, the properties here are, again, you'll notice these magnets are not quite as strong as the other magnets we're making, mainly because we still are only at about 60% volume of magnetic material. The rest is dead space. Yep.
So your surface looked very clean after that, Dr. Blade. Do you do any cleaning after?
Sometimes we leave the photoresist on from the DRE, and we can strip that off, and it helps lift off the particles. These very large 50 micron particles actually transfer very cleanly. They're pretty big.
So the 15 micron are also
15 micron is pretty clean. So I mean, this is not a doctored photo. I mean, this is just, that's what it looks like. But I will say this is actually the rough side of the wafer. This is the back side of the wafer. That's why it's not a dull finish and not a shiny finish. All right, so we did this. Okay, so the other thing, so here's where we were maybe 3 years ago. And so we kind of convinced myself we have a couple different magnetic materials, and now I want to make devices and things. And so, as I mentioned from some of the questions, we have a film on a surface, and normally we have to magnetize the whole wafer at the same time. And so we have a big fixture, and it applies a very uniform field. And so the whole wafer, we can make magnets, but they're all, say, north magnetized. I'd like to be able to create, take that film, say the cobalt platinum, and impress like a magnetic pattern. So it starts to look something more like a hard disk drive, where I can control the size and shape of the north and south poles and do more interesting field patterns. So how would I do that? We can look for some inspiration from a hard disk, but the problem is what we're trying to do is very different than a hard disk drive. Namely, we have much thicker layers, tens of microns compared to tens of nanometers. We are using much better performing magnetic materials. When we make a hard drive, we use a kind of semi-hard magnet, not a very strong ferromagnet. we're making much larger poles or bits, and we obviously want to do this in a batch fabrication process. We don't want to have to raster and read head around with the wafer, because that would take a long time to write the whole hard drive or the whole wafer. We quickly realized even if we're able to do this, we're going to have a problem because we don't have any characterization tools to measure that pole pattern at these size scales, and there's not a lot of commercial instrumentation out there to do that. The closest thing would be an MFM, magnetic force microscopy, but that's usually measures over maybe a very small 10 micron by 10 micron region, and it's not a very quantitative measurement. And so we need to develop metrology tools to do this. So one thing we created was a scanning Hall probe sensor. And so I'll talk a little bit about this. There's a little Hall probe sensor that sits on the top, and then there's a 2-axis stage or 3-axis stage that moves our sample around. And the sensor, if you zoom in, it's on a little circuit board. There's the little sensor we bought from a company. And down in the corner of the chip, there's the active area of the sensor. It's actually a 1 micron spatial resolution sensor. We get very high spatial resolution. We can control the fly height off the surface and raster it around over the
I
wafer.
have a question.
Sure.
What about your GMR reading head for this?
The GMR heads could work. The fields we get for some of our applications are fairly strong, 0.2, 0.3, 0.4 Tesla. And so a lot of the GMR heads are designed to measure very weak fields, and we would saturate a GMR sensor, for example. A Hall sensor gives a very large dynamic range in the sensor.
But now they use perpendicular model recording.
That's right.
The fields are not that small.
The fields depends on the material. The fields that the GMR head reads are certainly probably below 0.1 Tesla, I'm guessing.
But we have another option, move it away from the surface.
Sure. Agreed. We could retrofit it with the GMR sensor. Another thing we've done is magneto-optical imaging technique. And in this case, we don't have a sensor per se. We have a substrate which has a magic magneto-optical layer. This is this yellow layer here. We use polarized light, and we send polarized light, I guess this way, down into the substrate. And this magneto-optical material, as polarized light comes through, if the material is experiencing a magnetic field, it will actually rotate the polarization. And so the degree of polarization shift over the reflected light correlates with the sensed magnetic field. So here's my credit card information, if you'd like to write it down, imaged from this technique, and the different intensities of light that represent either a north pole or a south pole. We've further developed this technique where we can actually get quantitative 2D field mapping of the entire field pattern above the surface of a wafer. All right, so now on to how do we make what I call selectively magnetized film. I can tell we're running out of time. So we'll skip through some of this. We deposit our material, electroplate, our hard magnetic film like the cobalt platinum. We then pulse magnetize it uniformly north, and then we take a separately fabricated, what we call soft magnetizing head. This would be like a piece of iron. It could be a little iron foil, or maybe a microfabricated stencil on another silicon wafer. And this is a soft magnet. We bring it down and just put it in contact with it, and then we pulse a magnetic field downwards. When we do this downward pulse magnetic field in areas where the iron is, we actually get a field concentration. And the downward field underneath the iron is slightly higher than the field in the air gap. And so we tune that reversal field such that it's just enough to reverse the magnetic areas here, but the field in these air gaps is insufficient to reverse the magnet. So we can actually impress a pattern into the film. So to give you an idea of what that looks like, these are the optical images of the foil. This is just a 100 micron thick piece of iron. We laser cut like a stencil of just lines and stripes of different periods. We put that foil in contact with our layer, do this magnetization process, and we image now the north-south pole patterns in the resultant magnetized film. And so you can see very good, there's some dimensional control issues that I'll have to skim over. Over here you see the squiggle pattern. Some of this is the fields are getting slightly weaker, and it's some limitations of the magneto-optical imaging technique. Skip this. But the other cool thing is we can do arbitrary patterns. So here's the same laser foil. The black regions are areas that have been cut out from the foil, and we can create whatever your favorite logo of the day is, or whatever your favorite sponsor who's coming in that week. We can make a logo for them, and they're quite happy. So the color pattern here, again, yellow would be a north pole and red would be a south pole. And in the areas out here, we actually have kind of a low magnetization state in the film. There's a lot more details here that I can't get into in the interest of time. So let me shift gears and sort of close with some applications. And I'll show you how we're starting to use these materials in different application spaces. The first being actuators. So this was some work we did quite a while ago now. And it was really just to demonstrate that the thick bonded powder technology. And so what this is a silicon wafer, a cross section. We have the magnet is here in the middle of this PDMS diaphragm. So in the optical image, you'll see the PDMS is optically translucent. The magnet is here in the middle of the wafer. It's magnetized perpendicular, so it's just a little disc-shaped magnet. And then we put a coil around the periphery. And so in cross-section, the magnet is here. There's a coil that goes around, and we design it such that we get an out-of-plane piston-like motion from that actuator. So you could redesign that to be a speaker, a valve, a pump, a variety of different types of actuators with some more design. This is a picture of the process flow, just to give you some sense of how we would do this. Start with the wafer. We pattern the electroplated coils on the top. We spin on the PDMS layer, and the copper actually helps with the adherence of the PDMS onto the film, particularly near the edges of the membrane. We then etch a cavity in the back and do our packed powder process. We then pulse magnetize the magnet and then do a DRE etch to etch away and release the magnet so it can be free to oscillate. And this is a picture of the device compared to a quarter, so a fairly small, few millimeter diameter device. We tested this as an actuator. We did different designs, and it gives a typical second order response like you would expect, and we do a lot of reduced order modeling to describe the physics of this from a simple electromechanical model. But long story short, just to give you some sense, in the flat band down here, before resonance, the actuators, this is a plot of displacement, center displacement of the actuator is a function of current. So at fairly heavy currents, in this case half an amp, we get a micron of displacement. It's a lot of power draw, but these were just technology demonstrators where we just had only 3 turns of coil. We can certainly increase the number of turns, and we have done that more recently to get better performance. I won't talk about the micro speaker. We tested it as a little earbud or like for a hearing aid application as a speaker. These particular devices actually gave the right sound pressure levels but didn't have sufficient bandwidth for that application. Again, just to try them out. This was to help confirm some of our modeling. What we are working on right now is building something called a synthetic jet actuator. These are devices that interact with an aerodynamic flow. They're used today to cool LED lamps. There's concepts for steerable bullets and flow control over airfoils, particularly for micro-air vehicles, where these little actuators can be placed on the wing and they interact with the flow in a very nonlinear manner and control the flow over the wing. So what is a synthetic jet actuator? It's simply like this would be a cross-section. There's a flat plate with a hole in it, and then this actuator on the bottom moves up and down. It sucks in air and it ejects it out. And if you do this at the right frequency, you get these directional vortices, or what's called a synthetic jet. It feels like a continuous jet blowing out of the hole, even though there's no net mass transferred to the device. So the structure was an adaptation of the device I showed you earlier, and I had some pictures. I just didn't get them transferred over to my laptop. But what we're hoping to do is to build a synthetic jet actuator this is reference literature that has pretty good performance, but in the smallest package that's been reported to date. So they could actually put these little microchips onto other applications and then drive appreciable flows with projected velocities on the order of 20 meters a second, which is fairly consistent with macro scale devices. Another big area of interest has been vibrational energy harvesting. I use these as a mechanical to electrical generator. And so the traditional device, in an electrodynamic device would have a magnet and a coil, and so that functionally is very similar to what we had before. So we took the same structure I showed you before, and this time just shook it, and when we shake it, this center mass acts as an inertial proof mass, so we can test it as a vibrational energy harvester. Again, with no optimization. So the device does perform. This is a plot of microvolts per G of acceleration, so you can think of 1 G acceleration. We get about 12 microvolts generated, resonant frequency around 500 hertz. And at that acceleration level, we generated an amazing 23 picowatts of power, which isn't a lot, arguably. But we did demonstrate again that it's feasible to make fully microfabricated devices. And there's plenty of room for improvement. We've also done a multi-pole harvester. And again, I think I'm going to run out of time, so I'm going to skip over that. If you have questions, you can come back and talk. But this was showing our multi-pole technology, also for an energy harvesting application.
You have time to 5.
Till 5? Okay.
You can.
What is it, 4:50?
Yeah.
Okay. I want to talk about my favorite application, so I'll come back. The last thing I'll talk about is another project that is hopefully coming to kind of conclusion soon. I knew nothing about this. When I was in France, I stayed near this in Grenoble. This is a picture looking down from the mountaintop on this big facility here, which is called the European Synchrotron Radiation Facility. And this is something that if you don't know much about this, you think this is a big atom smasher type facility. It's something like that. But it's something that creates synchrotron radiation. So what is synchrotron radiation? Synchrotron radiation is a way to make very monochromatic, meaning single tone electromagnetic radiation. And we can make visible light, IR light, UV light, X-rays, gamma rays over a very large spectral window. Yes?
But it goes under different name. It's a free electron laser.
Free electron laser is a slight enhancement on this as well. There's some other lasing that happens in the free electron laser. There's very similar principles, for sure. So the basics of this is you take an electron beam and you fire an electron beam through a series of magnets. And these series of magnets are called an undulator or wiggler. And when the electron beam feels a north pole, it wiggles to the right. And when it feels a south pole, it wiggles to the left. So as the electron beam goes through, it basically wiggles. And as it passes through, because that electron vibrates back and forth, it actually emits a radiation, like a beam of light. If you make it visible light, or a beam of X-rays comes out the other end. And so this is a way that they make these, is with these big facilities, because you have to accelerate this electron beam up to nearly the speed of light, and then pass it through this undulator. Now, the wavelength of the radiated light that you get here is related to, or the energy, which is related to the wavelength, it's related to the energy of the electron beam, but also the pitch or the periodicity of that magnet array. A state-of-the-art undulator uses bulk magnets that they assemble together, and the period here is about 5 millimeters. So what would be considered very state-of-the-art in the physics community, beam physics community. So we have a project trying to figure out, can we make an undulator where this pitch is not 5 millimeters, but maybe 5 microns? And if we can make that pitch much, much smaller, for the same electron beam energy, if we pass through, we get even higher frequency radiation, or equivalently, we can make X-ray radiation by using a lower energy electron beam. So the idea, one motivating factor was to create high fidelity X-rays with a fairly modest electron beam setup. But with this micro-undulator technology, you might be able to get very high energy, high frequency X-rays. So we were working towards this from several approaches with collaborators at Georgia Tech. One way we were laser machining bulk magnets and actually basically kind of taking an assembly type approach where we would laser machine, you can see very carefully, 2 interdisciplinary arrays. One array would be a north pole, the other way would be a south pole. We would fit them together. And these fingers would create the alternating north-south, north-south, north-south cut. This would be one half of the undulator. We would have a second piece like this that we would sandwich over top of the other. And when they're sandwiched together, it looks something like this. Here's the upper piece, here's the lower piece, and then here's the gap. So that's the target. We need to shoot the electron beam through that, in this case, 200 micron wide gap. And this is doable. So we spent a lot of time designing the laser machining process, predicting the fields, measuring the fields from these magnets. This is actually experimental data of the magnetic fields along the length of where the beam would go, and looked promising. So what I showed you on the last page was we had a roadmap for getting smaller and smaller. One was using the laser cut magnets, which I just showed you pictures of. If you've been following carefully, we had visions of using our cobalt platinum films and the selectively magnetized stripes to do it at smaller and smaller scales as well. So our plans right now is we can come up with designs for what we call our mini undulator at a 400 micron pitch, and our micro undulator, which had a 50 micron pitch. And these are other beam parameters that make sense if you're in this high energy physics community. The undulators, once assembled, this one should give about a 1/4 Tesla field in the gap. This one about 0.1 Tesla. This impacts how many photons you get from the synchrotron radiation. So we partner with a number of different universities that have different beam lines. These are physics people who have either synchrotron type facilities or laser-based systems to create these very high energy electron beams, and we tried to test our undulator with their electron. So what I will say is we did some preliminary tests with Michigan, we got some photons, kind of demonstrated the technology, but their beam energy was not high enough to generate X-rays, which wasn't quite our goal. We have an experiment planned actually in May out in Stanford, the National Accelerator Laboratory called SLAC. Stanford's campus is over here. This is a highway. And so buried under the ground is this linear accelerator. So they start electrons down here, and they shoot them down this underground tunnel in the vacuum for 2 kilometers, and they're going to try to fire it through our 200 micron gap. And so there it is, and we have plans in May to go do this. And so if we're successful, what should happen is they get the beam fired through the gap, hopefully nobody hits the wall, and we should actually generate gamma rays from our device. And so the physics community is very excited about the technology because we think it could be some of the first demonstrations of synchrotron gamma ray radiation.
So I wonder how it works when you go out there. Do you work with the engineers? Do you get a time?
That's right. So we
How
actually,
does that work?
Yeah, the process is you actually file like an application. There was a period where they take experimental proposals, we write the proposal, and then they review them, they award them. And so basically now they cover all the expenses of the experiment. We just have to show up with our reports, and they have staff on site that helps us do the experiments and runs the physics. Yeah.
How long does the undulator have to be?
It's 2 centimeters.
Is that long enough?
It's long enough, yeah. So there's 100 periods, actually. So if you go here, there's 100 periods of magnets over a 2 centimeter distance.
Okay.
Let me make your life with it.
Sure?
You have periodic structure.
Yes.
Yes?
Yes.
And period is very small.
Yep.
And the field outside satisfies Laplace equation. If it's periodic in one direction, it exponentially behaves in another
That's
direction.
right.
So you have to have extremely narrow air gap.
That's right.
How you will position this?
Yep. So just for reference, the electron beam that they shoot has a full width half max of 2 microns. So they have extreme focusing magnets. And they narrow that beam down to a very pinpoint.
And beams that you will use is a sheet beam or pencil beam?
Pencil beam.
Pencil
It's
beam.
slightly elliptic in its shape, but the cross section, let's just call it a
Do you
circle.
know that it was programmed here about 30 years ago on FEL?
Yeah. There's lots of programs on FEL and other related
That
technologies.
is nothing else as FEL. Nothing, or you can call it any name you wish. This is a electron laser. It was very strong program here when
Okay.
we use short period electromagnet.
Electromagnets, right. There's a
You
group
can use
currently
simple technology to produce electromagnets.
That's right. I'd be interested to know more about that for sure. There's another group at UCLA that's trying to do this with a rather electromagnet, microfabricated electromagnet structure.
Simple technology can produce it. And it's controllable too, while in permanent magnetics is not controllable.
Right. So ours, the disadvantage is we can't turn it off. Thank you for making my life harder. All right, this is a picture of what it looks like underground. So maybe I'll stop here because I've been talking for a good 50 minutes now, and maybe open up the floor if there's any other questions. I do want to acknowledge numerous students, postdocs. I have a lot of undergrads that work in my lab. I think it's very similar to what I've seen here, and obviously all the different funding sponsors who funded various aspects of the different things I've showed you today. So I appreciate your attention and be happy to take any questions.
All right, very interesting. Any questions?
Sir?
Did you have any difficulty convincing your clean room staff to let you do that deep reactive ion after you did the bottom
So that part of the wafer is covered with photoresist. So no, they let us do it, and we still do it today.
Sorry, we didn't hear you.
So you've stuck magnets?
We did that.
You're worried about the magnets or the particles?
Covered by
Both.
photos.
Yeah.
I mean, you have them bonded, you already have them bonded.
They're already bonded in place, and they're covered by photoresist, thick photoresist.
Yes.
They're kind of safe.
And there's a debate about how much contamination it uses to the resist, but that's
Did you do that with plated magnets or?
plated magnet.
When you use this material, it's What about the standard cable?
It's a metal. It's very thin.
So it's, from this point of view, it's susceptible to any current,
Correct.
which can degrade the performance of it.
Are you talking, so what application are you thinking?
You're right, it depends on application, but in application when there is a moving parts like your electron beam and all these.
Yeah, so the one concern with the electron beam project is when the electron beam goes through, it creates this like a wake. There's some eddy current generated as the electron goes by. In the macroscopic experiments, they use the rare earth materials, and the laser machine structures, we also are using the same material set. We've just machined it to much finer structures. So for the samarium cobalt magnets, we hope, well, we have preliminary data that shows that that's not going to be an issue. With the cobalt platinum, it's another, that's more concerning because it is conductive. We've had a lot of discussion with people. We don't have the expertise to model that, but we didn't get to that point anyway. With the cobalt platinum microscale emulator, unfortunately the program got canceled. So we had to stop work on it. So we're hoping to get this last experiment with the laser machine structures, which is the samarium cobalt magnets.
All right, more questions.
So the powder technology is very exciting, and one can do some really crazy stuff with that. So where are some of the limitations, and where do you think you will get at?
Yeah, so we're also pretty excited about the powders. The thing I like about the powders is it decouples, the magnetic materials are made by somebody else, right? And we just have to, our job is to now microfabricate the structure. So we decouple the magnet synthesis from the magnet dimensional structure. And so we've done magnets hard and soft. The biggest challenge is to actually get a high volume fraction of magnet. And so this comes down to control over the particle morphology and the dispersity, monodispersity of the particle sizes, and there's different tricks and games you can play. We haven't exploited that fully, but to get good performing magnets, you try to get a high loading fraction. The typical numbers we get are 50 to 70% by volume, and that's pretty good for most applications. So we're achieving 50 or 70% of the remnant magnetization, or the potential magnetization, the total moment of that.
Because I think it's the best technology for some of these flexible substrates, and has a lot of potential for durability.
So we've done that embedding polymers and soft materials to make flexible magnets. We don't have to make straight wall DRE trenches. We can make all sorts of more complicated structures.
Yeah, I was thinking of like sharp edges, how do you do
Right.
it? Yeah.
So the fidelity, the dimensional fidelity that you can achieve depends on the particles you're using. And smaller powders are better. But again, with the rare earths, you generally can't find them much smaller than 2 microns because of oxidation problems. Yep.
In this, I will call them ETL, electron laser.
Sure.
You maintain the constant period,
In our structures, the period is set, yes, but you
but
can't change it.
electron beam as it moves, it radiates, yes? So it's energy losses.
Very slightly, very slightly. It's something like.
So you're not
minus
dealing
12
with a
efficiency.
high power.
What's that?
It's a very low power, actually, yes?
The number of photons we get, the flux is very low.
There is high power generator and low power generator. So in low power it may be not bad. In high power there was
Yeah, that's correct. That's the difference between our potentially tabletop solution and a $3 billion 80-acre.
But it's not your job, for instance, for this to operate, it should be proper bunching of the electrons of the beam.
Yeah, that's somebody
You're
else's
not
problem to
doing
solve. There was multiple teams, and most of them were physicists, and they had all that quote figured out. Right? So my job was to show up with the magic undulate, and they knew how to do that. So that was the agreement. Any questions from the students? Yeah.
Do you have some other device structures? Because I noticed you went directly to the current and iron based structure, but do you have some vision for like the permanent magnet on magnet structures?
So the devices I showed you, actually, the magnet was always a permanent magnet. I didn't show it, the blue magnet of that piston type, but that was actually a permanent magnet in the center.
Okay.
So it's permanent magnet coil interaction. So maybe that answers your question. But yeah, we have a lot of projects right now with some biomedical partners to use micromagnet arrays to tag the nanoparticles out of biological fluids, a whole variety of things that we can do with these. The ability, what we have now really is to create, with some limitations, lots of limitations, fairly complex magnetic field patterns with microscale feature sizes. And so that's a really enabling technology to have. And we're still discovering new applications all the time of what this could be used for. And if you have ideas, I'd definitely be glad to talk with you as well. Yeah.
So the energy harvesting applications that you look, how do you process the power? How do you condition the power particles? Like, because like tiny, big power.
Yeah, so this is, we could have a whole discussion over here about it.
Yeah.
So that's, I've been trying to stop working on energy harvesters for 10 years, but people keep throwing money at it, so you keep working on it. So, yeah, I agree. I don't know what applications, it's very selective applications that could make use of picowatts of power. And if there is an application that could run on picowatts of power, I could give you a microscale battery that's smaller than my energy harvester with no moving parts, and it would probably last you 20 years. So there's still applications I can't think of where an energy harvesting solution makes sense from the power density, energy density, and cost.
Anyone from NSA here?
So very good, very, very. It's cool. It is very cool technology, and it's one of those things I feel has been a little bit oversold. People hear energy harvesting, and the first thing they think is I'm going to walk around and keep my cell phone charged. And the gap between that and what we can actually harvest is orders of magnitude difference. So low power wireless sensors, these kind of things is possible. But the main thing with energy harvesters is they're power limited. So if you need big power, you need a big harvester. And people don't want a big harvester, they want a little harvester, and little power. So there's just a lot of trade-offs.
All right, any last questions?
You're concerned only with permanent magnet material or soft magnetic material you can put on a silicon chip.
We do soft magnetic materials as well. We can talk about them here. We do electroplated, nickel, iron, and cobalt.
And you can make inductor on silicon chip.
David's PhD thesis was one of the first one that demonstrated that exact concept. I agree.
There's a lot of people before me.
Yeah, but I think it was.
So we did,
It was the first.
we did magnet material. We did wafer bonding with embedded metals and other things. So there was a lot of our fabrication that didn't work.
All right, let's thank David.